In the last lecture we had answered the question, why do we need optical communication, that is why do we require light waves for telecommunication, and the answer we found is that we utilize carrier wave communication through EM waves for telecommunication purpose. And we had seen that in carrier wave communication, if we increase the frequency of the carrier, the data transmission rate can be increased, the bandwidth of the system increases. Light waves have much larger frequency as compared to the microwaves and radio waves. That is why light waves can give you enormous bandwidth, very large bandwidth, and this is the primary reason for using light waves for high data rate communication. If we want to use light for communication, then we need to guide light across curves and corners in the same way as copper wire conducts electricity. So, now in this lecture we will look at the structure which carries light along it around all the curves and corners, and this structure is called optical fiber. We are going to look into the salient features and characteristics of optical fiber in this lecture. So, what plan we have for this lecture? We will look at the structure of a typical optical fiber, which is a step index fiber. Then we will understand what is the need for studying light guidance in an optical fiber. What is the ray theory of light guidance, which is a very simple theory to understand light guidance in a fiber. Fiber guides light through two types of rays, one is meridional rays, another is skew rays. Then what is the light gathering capacity of the fiber? What is the numerical aperture of the fiber? Then there are different type of fibers which have refractive index variation in the core, they are known as graded index fiber, and we would look into how rays go in graded index fiber, what path they follow. So, let us first look at the structure of a typical optical fiber. This fiber has a high index core of refractive index N1 and radius A, which is surrounded by a cladding of refractive index N2 and radius B. So, if I look at the refractive index variation in this region, then in the core, which is defined by 0 is less than R is less than A, the refractive index is N1. In the cladding, which is defined by A less than R less than B, refractive index is N2, and this is the refractive index profile of the fiber, NR as a function of R, where the refractive index is N1 from 0 to A and refractive index is N2 for R greater than A. For simplicity, I have considered here infinitely extended cladding instead of a finite cladding, because the cladding is much larger, cladding dimensions are much larger than the dimensions of the core. So, we can consider it to be infinitely extended. The index difference between the core and the cladding is defined by a parameter relative index difference, delta is equal to N1 square minus N2 square over 2n1 square, and for practical fibers n1 is close to n2, the difference between n1 and n2 is small and they are known as weakly guiding fiber. For such fibers delta can be approximated by n1 minus n2 over n1. Now the question is, what is the need for studying light guidance in the fiber? Well, when we send data through optical fiber, it is sent through train of optical pulses, and we need to know what happens to these pulses when they travel through optical fiber. So, studying light guidance through optical fiber and its transmission characteristics enable us to understand, number 1, what happens to light pulses when they travel through optical fiber, and number 2, how can we optimize fiber parameters as per our requirements. How light is guided through optical fiber? Well, to understand that, let us have a look at this, which is a lighted fountain here, and what we see that light is placed somewhere here, light source is placed somewhere here, and these streams of water, they capture light, they are lighted all over. How do they capture light? How do they guide light along the stream? How the light is guided along the stream? Another thing we can look at is, we can perform a very simple experiment in which we fill a transparent bottle with water, pierce a small hole in the bottle and let the water stream come out. Now, if I launch light from a laser pointer onto this hole, then what I see that here the light travels in a straight line, but here this stream of water captures light and light is guided along the stream. How this light is guided at all? Well, the answer is, the mechanism of guidance here is total internal reflection. What is total internal reflection? So, to understand that, let us have these two media N1 and N2. This is a denser medium, this is a rarer medium. So, N1 is greater than N2. Now, when a light ray is incident on the interface of these two media, the light ray gets refracted. If I increase the angle of incidence from the normal, then since it is going from denser to rarer, it moves away from the normal. Okay. So, if I increase the angle, it will further move away from the normal, and at one particular angle phi c, this refracted ray basically grazes the interface between the two media. Now, what is this phi c? This phi c is called the critical angle for total internal reflection, and it can be given by sin inverse n2 over n1. Now, if I incident a light ray which makes an angle larger than phi c, then this light comes back into the same medium. This is known as total internal reflection, and the condition for total internal reflection is that phi should be greater than phi c, the critical angle. This is one very simple experiment that you can do. You can fill a transparent tank with water and then you send the laser beam at different angles, and you find that if the angle of incidence is larger than the critical angle, there is total internal reflection at the interface of water and air. Now, if I look at the ray theory of light guidance in optical fiber, then light is guided by total internal reflection at core cladding interface. So, if I launch a ray of light into the fiber, it goes like this, and if this angle which this ray makes with the normal to the core cladding interface is larger than the critical angle, then it will be totally internally reflected and it would be guided. What we can see here is these rays, they cross the fiber axis and these are known as meridional rays. There can be another possibility that depending upon the launch conditions, a ray can never cross the fiber axis, but it will be totally internally reflected, it will undergo TIR, but it will follow a helical path, it will never cross the fiber axis. If these would be clear when we see the transverse cross section of the fiber. So, if I look at transverse cross section, so these rays go like this, okay, and they never cross the axis. So, these rays are known as skew rays. So, light guidance takes place via meridional rays as well as skew rays in an optical fiber. Now, let us look at light guidance by meridional rays. So, if I launch light at various angles into this fiber, this is a longitudinal cross section of the fiber, then what happens is that the rays launched at different angles will be guided through successive total internal reflections. Now, the question is, are the rays launched at all the angles guided, or there are only certain range of angles that would be guided? To understand that, let us apply the condition for total internal reflection in the fiber. So, again this is the longitudinal cross section of the fiber. You have a core with refractive index N1 and cladding of refractive index N2, this is the fiber axis, and the refractive index of the outside medium is N0. Now, let me launch a ray from outside medium onto the input end of the fiber, let us say at an axial point, and it makes an angle I from the axis of the fiber. Now, when this ray enters the fiber, it is refracted, and let this refracted ray make an angle theta from the fiber axis and correspondingly an angle phi with the normal to the interface of core and cladding. Now, from Snell's law, I know that N0 sin I should be equal to N1 sin theta, and the critical angle at core cladding interface is given by sin phi c is equal to N2 over N1. Now, it is clear that for TIR at core cladding interface, this phi should be greater than phi c, and correspondingly pi by 2 minus theta should be greater than phi c, because phi is equal to pi by 2 minus theta. So, if this phi is greater than phi c or this pi by 2 minus theta is greater than phi c, then this ray will undergo TIR, successive TIR at core cladding interface and would be guided. This condition for total internal reflection can also be written as theta is less than pi by 2 minus phi c, and now if I take sine of this, then sin theta should be less than cos phi c, and if I multiply it by N1, then N1 sin theta should be less than N1 cos phi c. Since sin phi c equal to N2 over N1, so cos phi c would be equal to square root of 1 minus N2 square over N1 square, and n1 sin theta is equal to n0 sin I. So, this equation will now give me n0 sin I should be less than n1 square root of 1 minus n2 square over n1 square, or sin I should be less than square root of n1 square minus n2 square over n0. So, for a limiting case, if I consider the limiting case, this sin I max is equal to square root of n1 square minus n2 square over n0 defines the maximum acceptance angle, which means that if this I is less than I max, then there would be total internal reflection at core cladding interface and light would be guided through optical fiber. If I take outside medium as air, then n0 is equal to 1 and sin I max is equal to square root of n1 square minus n2 square. Now, we have seen that sin I max is given by this, but the question is, if n1 square minus n2 square over n0 is greater than 1, then what would be I max or sin I max? As I know that sin I max cannot assume values greater than 1. So, even if it is greater than 1, then sin I max will be capped at value 1, because I max cannot be greater than 90 degrees. So, now if I launch a cone of light into the fiber, then what I see that all the light which lies in the cone of semi vertical angle I max will be guided through the core of the fiber, and the light which makes angles larger than I max would be refracted. I can see it in this way also, that if this cone of light has semi vertical angle which makes which is smaller than I max, then this light will be guided through total internal reflection, and if I launch light in this region where the angles are larger than I max, then this light will be refracted and it will not be guided through optical fiber. The second kind of rays which we talked about is skew rays. What is the condition for total internal reflection and light acceptance angle for skew rays? For that, let me launch a ray of light somewhere here onto the fiber end, and it makes an angle I with the fiber axis in the outside medium n0. When it enters the fiber, this ray makes an angle theta with the longitudinal direction of the fiber, and it is reflected here. It is incident, it hits the point Q at core cladding interface and then it is reflected. Let me make this plane, consider this plane which contains this incident light and reflected light, okay, which is represented by green here, okay, and this is the normal, QT is the normal at the core cladding interface. And then let me also consider another plane which is a longitudinal plane, but which contains this line, this longitudinal line which passes through Q. So, basically this plane makes an angle alpha from this longitudinal plane. If I consider a transverse plane here which is STQ, then this transverse plane makes an angle phi from this incident ray, and this is the reflected ray that also makes an angle phi with this. Now, what I can see here is that this PQ cos phi is nothing but SQ, and QT cos alpha is also SQ. I also find that this PQ sin theta is QT. So, if I consider these two, then I find that this SQ is nothing but PQ sin theta cos alpha, because QT cos alpha is equal to SQ and QT is PQ sin theta here. Now, if I consider these two equations, I compare them, then I immediately get cos phi is equal to sin theta cos alpha. So, in this way what I have got? I have got phi in terms of theta and alpha. Theta is related to I, so I can relate it to I, and then I can find out what is the condition of total internal reflection. I know that for total internal reflection phi should be greater than phi c, and if I consider this limiting case for TIR, then phi is equal to phi c, correspondingly theta is equal to theta c, and let us say I is equal to I max. Then I have from here cos phi c is equal to sin theta c cos alpha, okay, and since phi c is equal to n2 over n1, it gives me sin theta c cos alpha is equal to square root of n2 square over n1 square from here, okay. So, let me write this one down, which I will use later also, that cos phi is equal to sin theta cos alpha. So, cos phi is equal to sin theta cos alpha. Well, now since from Snell's law I have already seen that n0 sin I should be equal to n1 sin theta. So, n0 sin I max should be equal to n1 sin theta c correspondingly, and hence sin I max would be equal to n1 cos phi over n0 cos alpha, because sin theta is equal to cos phi divided by cos alpha. So, and cos phi is square root of 1 minus n2 square over n1 square. So, this gives me sin I max is equal to square root of n1 square minus n2 square over n0 cos alpha. You just recall that in case of meridional rays, this sin I max was square root of n1 square minus n2 square over n0. Now, I have an extra factor of cos alpha in denominator, and cos alpha has maximum value 1, okay, and that is the limiting case. So, since cos alpha is less than 1 for skew rays, so skew rays are accepted for TIR at larger angle than the meridional rays. But what happens is that these skew rays are confined to the rim of the fiber, they never cross the axis, and therefore, they do not fully utilize core for light guidance, and because of this they are not very important to be considered in optical fiber design and communication. Now, let us look at numerical aperture of the fiber. We have seen that the rays launched into the fiber are limited to a maximum acceptance angle for guidance through optical fiber. For meridional rays, this acceptance angle is given by sin I max square root of n1 square minus n2 square over n0, and for skew rays it is square root of n1 square minus n2 square over n0 cos alpha. Now, if outside medium is air, then for meridional rays sin I max is equal to square root of n1 square minus n2 square, and this represents the numerical aperture of the fiber. So, if the fiber is in air, then what is the maximum acceptance angle? That gives you the numerical aperture of the fiber, because this maximum acceptance angle basically tells you the light gathering capacity of the fiber, and that is why it gives you the numerical aperture. It is known as numerical aperture of the fiber. So, numerical aperture, or in short NA, is square root of n1 square minus n2 square, and it purely depends upon the refractive indices of the core and the cladding. If you remember that I had defined relative core cladding index difference delta is equal to n1 square minus n2 square over 2 n1 square. So, I can represent this NA also in terms of delta. So, you get it as n1 square root of 2 delta. Let us consider an example. For a typical glass fiber with n1 is equal to 1.45 and n2 is equal to 1.44, delta is equal to about 0.69% and Na is equal to 0.17. The maximum acceptance angle in air is can now be given by for meridional rays as I max is equal to sin inverse N A over N0, which is about 10 degrees, 9.8 degrees, and for skew rays for alpha is equal to 40 degrees, it is about 12.8 degrees. If I put the same fiber in water where the refractive index is 1.33, then for meridional rays I max becomes 7.3 and for skew rays it is 9.6. So, what do I see here? That for any given outside medium, the skew rays have larger I max than meridional rays, and if I change the outside medium, if I increase the refractive index of the outside medium, the light acceptance angle goes down. If I consider an unclad fiber, then N1 is equal to 1.45 and N2 is 1, which is basically air, then delta is 0.26 and square root of N1 square minus N2 square is equal to 1.05, which means Na should be equal to 1. Okay. This shows that the maximum acceptance angle for guidance can be close to 90 degrees, because Na is equal to 1, sin I max is equal to 1. Clearly, this fiber would have much more light gathering capacity as compared to cladded fiber. Then the question is, what is the need for cladding? Okay, and we will answer this question later in subsequent lectures. Now, let us look at the limitations of ray theory. What are the limitations of ray theory? Well, ray theory is basically geometrical optics, and geometrical optics is valid only for dimensions which are much larger than the wavelength of light. So, ray theory breaks down when we consider fiber whose core is of the order or to the comparable to the wavelength of light. Second thing, that it will not tell you the discrete modes of the fiber. As we will go along, we will learn that the fiber supports certain discrete modes of propagation, but ray theory cannot tell you about discrete modes of the fiber. Third thing is, when light is guided through optical fiber, some light also extends to the cladding, and ray theory cannot explain this. So, these are some limitations of the ray theory. Then, apart from step index fibers, there are graded index fibers, where the refractive index of the core is not uniform, it varies with r, the radial position. And a convenient way of defining this radially varying refractive index is using power law profile, which is given as nr is equal to n1 1 minus 2 delta r over a to the power q whole to the power half in the core r less than a, and it is equal to n2 for r greater than a in the cladding. This q is nothing but profile parameter. It basically governs the index gradation. Let us see what does it mean. So, if I put q is equal to 1, then the refractive index profile would be something like this. In the core, as you move away from the axis, the refractive index will gradually decrease, and this decrease is linear. This is also known as triangular profile. If q is equal to 2, then this decrease is like this in parabolic fashion. Then this fiber is also known as parabolic index profile fiber. And if q is very large, if q is infinity, then this is nothing but a step index fiber. So, very large values of q will give you a step index profile. How the ray paths look like in a graded index fiber? If I have a uniform medium and I launch a ray of light from here, it goes straight. But in a graded index medium, there is change in refractive index. Here the refractive index is larger, then is smaller, then is smaller, then is smaller. Then what happens is, if you consider an interface here like this, then it will move away from the normal, then here again away from the normal, here again away from the normal. So, light will not go straight, but it will be bent. So, it will follow a curved path, and this is the ray path in a typical parabolic index fiber. If the refractive index varies parabolically away from the axis, then the ray launched into the fiber follows a sinusoidal kind of path. So, the ray paths are curved. So, in this lecture, what we have understood that how light is guided through optical fiber via meridional rays and skew rays, what is the condition for light guidance, what is the light gathering capacity of the optical fiber, what is the numerical aperture of the fiber, what happens to the numerical aperture when the outside medium's refractive index changes, and what are graded index fibers. Thank you.